You don't have to list them all there. If you know what group 1 is, that's fine. You don't have to list them out one by one. Okay. They have kind of a silvery appearance. Okay, not too shiny, but they do have some shine to them. And these are the really soft metals. We saw a picture of one last time that you can kind of cut with a knife. Okay, so you'll see the group 1 metals are kind of silvery, a little bit shiny, and they're really soft metals. These are not found in nature as what we considered free elements. Okay, so if you're walking, you're not going to find a chunk of sodium just lying on the ground, okay, or a chunk of lithium or whatever it is. Do you have any idea why that might be? Yeah, William, what do you think?
They react with water.
They react with water. And how do they react with water? Violently. They go boom, right? So any source of water, it's going to blow up, right? Reactive, okay, especially with water. Okay, they have one valence electron. Have you heard the term valence electron before? Okay, good. So that means outer shell electrons, things that are not full. They don't have a full shell. So it's easy to remember valence electrons by group numbers. So group 1 has 1 valence electron. Group 2 has 2 valence electrons. Group 13, or group 3 as I was taught, group 13 has 3 valence electrons, and so on and so on and so on. Okay, so it's easy to remember valence electrons as we move across the periodic table. That's another reason that it's handy for us that they're arranged that way. Okay, so valence electrons are number of electrons in our outer shell. We're going to watch a quick video here about the reactivity of the group 1 alkali metals because we'll see lithium, sodium, and how they... So we go alkali metals, now the alkaline earth metals. Okay, alkali metals are group 2. Again, you don't have to write down individual elements. If you know where group 2 is, you can find it on the periodic table, and you're good to go. These are tougher, they're more dense, and they're stronger than the alkali metals. So they start to inch into the realm of what we think more of as metals. Okay? It's not all that usual for us to think of metals as being able to be cut with a butter knife. So this is more inching into that realm of what we would consider metals. Okay? They have higher melting points. So a higher melting point, what does that mean for us chemically or about the structure of that metal? What does that tell us? If we have a higher melting point, what's that tell us about the structure of that metal? It's what? It's more solid, okay.
Is it denser?
A little bit more dense, that's right. It tells us that the bonds between those metal molecules are really strong, right? A higher melting point means we need more energy or more heat to go into that metal to start to break those bonds apart. Does that make sense? So a higher melting point means stronger bonds. These are less reactive than alkali metals, so we're not going to see a big explosion with water. What's a metal in group 2 that you would be pretty concerned with if we had a reactive quality? Magnesium, calcium, right? Calcium is something you drink. Okay, it's in your milk. If it has explosive qualities, right, we'd have a problem. Okay, so these are much less reactive. We're obviously not drinking little metal flakes, okay? Let's get that straight. But those calcium molecules in there, we can't have that reactive, crazy quality, or we'd have big problems, right? Same with magnesium. You have a lot of magnesium, supplements. Magnesium's in a lot of supplements, vitamin type stuff. So potassium's in group 1. So we still do take potassium.
Isn't it in bananas?
Yep. These are less reactive than the alkali metals, but they're still too reactive for us to be found in nature. Okay, so that means they're not going to have that explosive quality to them. We're not going to have a big flame and a big explosion, but they're still going to react quick enough because of their number of valence electrons, which can you guess is 2. Good. Okay, 2 valence electrons in their outer shell. So we know group 1 Easy to remember, has one valence electron. Group 2 has 2 valence electrons. Okay? Is that what you see floating in your milk? No. Okay, good. Right, we hope not. Okay, so the transition elements come next. We're working our way left to right across the periodic table. The transition elements are what group of elements? Does anyone know? Yeah, they're like in the middle, right? Those 10 groups that are right in the middle of your periodic table. We haven't quite reached the metalloids yet, but it's that group of transition metals right in the middle. Okay, those 10 groups that are right in the middle where we split. Okay, so the transition elements are groups 3 through 12 technically. Okay, and we more often call these transition metals because they still contain all metals. We're not inching into the metalloid world yet, still metals. Okay, these have very typical metallic properties. So if you don't have your periodic table out yet, why don't you go ahead and grab that so you can have a little bit more quicker access to that. Then I want you to look through the transition metals and see what are some metals that are in that transition set that jump out as you as super common. Ones that we really think of as common metals. Iron, titanium, nickel, copper, gold, silver. Lead is not quite there. Lead's in 14. But a lot of the typical metals we think of as true metals, right, are in that transition metal section of the periodic table.
What about like the group that's in 3?
The group that's in 3, but they're, okay, those are in a different series called the lanthanides and actinides. We're going to talk about where they go. Yeah. So these typical metallic properties mean they're going to go along with what we learned about metals really well. Okay? They're good conductors of heat and electricity. They have really high shine. And they're less reactive than our other first 2 groups. Okay, so our first group 1 and 2, even though they're metals, they behave a little bit differently, right? We usually don't think of metals as lighting on fire when they touch water, right? So these transition metals act a little bit more like the way we think metals should act. Many of these are stable enough to exist as free elements. Okay, so this is where we find the true metals, and this is where we're able to really work with them in the metal context that we need to work with them in. Okay, really strong, really tough, good conductors of heat and electricity, non-reactive. Those are the things we need out of metals. Okay, ductile. What is that? Sorry, what do these 2 mean? Ductile and malleable. Ductile means a wire, good, and malleable means what? Yep, we can hammer it into a sheet. It's pliable, it's movable, good. Okay, the thing about the transition metals is that they don't follow patterns for valence electrons like the other groups do. So these have a variety of number of valence electrons, and that's a little tricky for us to wrap our brain around, but they don't follow the rules like the rest of the groups do. So these are ones that if we needed another number of valence electrons, we kind of just have to look it up. Okay? It's not one that follows a particular pattern or anything like that. So not anything that you'll need to really be able to recognize. We'll start working with some of the transition metals enough that you'll get familiar with their charge and their number of valence electrons, things like that. But it wouldn't be something that you would need to recognize a pattern within. Okay? Okay, moving now over a few rows to group 16. Okay, this is called the chalcogens. Chalcogens. And these are group 16. So what elements are we looking at here?
Oxygen.
Good. Oxygen, sulfur, selenium. Okay, so these are the oxygen family, group 16. Okay, so we're skipping 13, 14, 15 for right now. We're going to talk about the chalcogens and then we'll look back a little bit. Okay, group 16 are fairly reactive elements. Okay, they like to be social. They like to hang out with other elements, right? However, these guys have kind of a wide range of properties, a wide range of chemical properties. And I want you to look through group 16, and I want you to think about why would this group have a wide range of properties. Okay, look through group 16 and see what you notice, what happens as you go down group 16. Okay, yeah, Colin, what do you think?
There are metalloids, nonmetals, and metals.
Exactly. We have nonmetals in oxygen and sulfur. We have metalloids as in selenium. I think selenium is a metalloid, and tellurium. And then polonium, I'm not sure if it's considered a metal or a metalloid, but we're changing completely types of elements as we go down the group. So we have a lot of different properties within that group. Okay, oxygen's a gas. The rest are solids at room temp. Yeah, okay. These groups, okay, or these elements within this group tend to bond with metals. Okay, so oxygen, sulfur, selenium, tellurium, those will tend to bond with a metal. Okay, they're reactive enough to go bond with a metal. Many of these compounds are not soluble in water. What does it mean to be soluble?
It dissolves.
Yeah, it has to be able to dissolve. Okay, so these are not soluble or insoluble in water, so they're not going to dissolve. Okay. We just talked about they can be nonmetals, metalloids, or a metal. Okay, so I accidentally miscategorized selenium. Selenium's a nonmetal. Okay, and if you want to just kind of note that on your periodic table, that's fine, or if you want to write it down, that's fine. And then even underneath that is a man-made element. Okay, so we have nonmetals, metalloids, and man-made elements even farther under that in group 16, which is number 116, livermorium. So we understand that group 16 has 6 valence electrons. Group 15 would have how many valence electrons? 5. Group 14 would have 4. Group 13 would have 3. Okay? So we take out that transition metal 10, and we can name our valence electrons that way. Okay? So group 16 has 6 valence electrons. Next is the halogens, my favorite group. Okay, the halogens are my favorite. I don't know why. Okay, but these are group 17. Fluorine, chlorine, bromine, iodine, astatine. These are the most reactive non-metals. Okay? Most reactive non-metals. So we don't know if we really have a judge or a verdict between which is more reactive, the group 1s or the group 17s, but these are the most reactive non-metals that we'll look at. Okay? And usually they form salts. And that's a specific type of chemical compound, not just sodium chloride that you put on your food. Salts are a wide range of chemical compounds. But usually they form salts, and those are formed with group 1 or 2 elements. Okay, so elements from group 1 or group 2. A common one, a common salt that we do call salt is sodium chloride. So where's sodium coming from? Group 1, and chlorine is in group 17. Okay, so you'll see a lot of combinations between group 1 elements and group 17 elements, or group 2 and group 17. Okay? Can be gas, liquid, or solid. As we look down that group 17, you can see fluorine and chlorine are both gas at room temperature. Bromine is liquid at room temperature. And iodine and astatine are solid at room. Guys, you could have guessed have 7 valence electrons. So what is it about this group 17 that makes them so reactive? Anyone have any idea? It has something to do with their 7 valence electrons. Let's see if someone else. Yeah, Maria, what do you think?
If they have 8, then they won't have 8.
That's right. They want to have 8 electrons, which is called an octet. Right? They want to have a complete octet to be happy. Right? So if they have 7, would it be easier to get rid of all their 7 or to just take one from somebody else? Take one, okay? Or invite someone over to bond with them, okay? It's much easier to do that. So 7 valence electrons are very reactive because All the group 1s, think about that. The group 1 elements, they've got 1 valence electron. Is it easier to get 7 more or just give away that outer one? Yeah, give it away, right? It's easier to give away 1 than to find 7 new friends, right? You can kick 1 out, or you can find 7 new ones. It's easier to just get rid of the 1, right? So that's why group 7 and group 1 bond so easily, because group 1 wants to get rid of their electrons, group 17 wants to take 1, and so they complete each other, okay? All right. Usually these are too reactive to be found in nature, so again, they're going to bond with anything and everything, so they're rarely going to be found alone, right? These are the social butterflies of the periodic table, okay? These guys are not reactive with water. Okay, they're not going to have any sort of heat reaction or anything like that to be harmful in water. So think about the top 2 elements in group 17. Do we see those in water often? Right? Fluorine, or the ion version, fluoride, is usually found to help what? Your teeth, right? We put it in the water to help our teeth. So that's good that it mixes with water. Chlorine, where do you put that with water? In pools, right? So you see that. So we, again, hopefully we're not having reactive properties with chlorine in our pools. Okay. Okay, last group we're going to talk about really in depth here is the noble gases, which are group 18. Good. Very far to the right. These guys are super unreactive. Okay, super unreactive. Can you take a guess as to why they're unreactive? They already have 8 electrons, right? Their life's complete. They don't need nobody else, okay? They got enough. They don't need anything else, okay? So these are the non-social butterflies of the periodic table, okay? All of these are gases at room temp. Shocker that the noble gases are all gases, right? All gases at room temperature. They have a full outer shell, which we said contains how many electrons? 8. Good. 8 valence electrons. So, you'll hear neon, argon, krypton, and xenon. Right? We think most commonly of neon to represent neon lights. All 4 of those can be used in neon lights, surprisingly enough. But most often we think of neon. Okay? Any other questions about the noble gases?
How do they change the color of neon lights?
I don't know that. You're stumping me today, Ethan. I got 2 questions I gotta look up for you because I don't know the answer. I don't know the answer to that. Okay, there's 2 other parts of the periodic table that we want to talk about, and these are the lanthanides and the actinides. Okay, does anyone know where on the periodic table the lanthanides and the actinides are? They're the bottom. Okay, so the lanthanides start with La, right? That's how you can remember lanthanides and actinides. Okay, and where they fit in is right up here in this blank spot here. Okay, they really fit right here. That's where their characteristics go. But we wouldn't be able to fit it on a sheet if they really went where they're supposed to go, so they just pull them out and bring them down. Okay? So the lanthanides are atomic numbers 58 through 71, okay? Not including lanthanum and actinium. Okay? These are shiny metals, and they're similar reactivity levels to the group 2 metals, the alkaline earth metals. Okay, so the lanthanides are the top row there of that bottom pulled out section. The actinides are the ones right underneath that. They start with actinium. Their numbers 90 through 103, not including actinium. Okay, so sometimes you'll see lanthanum and actinium still up in the regular periodic table, and then the numbers after that are pulled down. Sometimes you'll see lanthanum and actinium pulled down with them. It doesn't really affect what we're doing a whole lot. Okay, these are all radioactive elements, so these are the dangerous ones. And most of these are man-made. Okay, some are found naturally, but most are man-made. So neptunium over are all man-made elements. Okay, so I'm going to show you a picture of what it would look like if the lanthanides and the actinides were put in the regular periodic table, and you'll see it throws us off a little bit. Okay. That's what it would look like if we kept the lanthanides and the actinides in there. Okay, so it's harder to see group numbers. It's spread out a little bit. It would be hard to fit on a sheet of paper, so they just pull them down and save some space to help us out there.